This is the Earth Science Classroom. Welcome back to the channel. This video is on earthquakes. We are looking at reviewing for an earthquake test, looking at different topics, different subjects, different parts of seismology and earthquakes. This goes along with what we do in class with my students, whereby we have a unit length of about 15 lessons. Each one's an hour, so that equates to about 3 to 4 weeks of work in class, including homework, labs, and review day. So this is the online review video that accompanies the lessons and the worksheets and labs for the students to use to get ready for the test on earthquakes. Here is a list of topics and content we're going to look at in this video. We're going to start at the top, which is the plate tectonics and convection currents, and work our way down through the logical progressive sequence of trying to build our knowledge and understand how earthquakes form and the different parts of seismology based on the foundational knowledge of stress, strain, and deformation in crustal rocks. And we're going to finish up looking at earthquake hazards and the potential dangers that are associated with earthquakes, both primary and secondary hazards. So what I want students to understand is where the original starting point is for earthquakes and where it all begins. Now, I like to start with the plate tectonics and convection currents because we did that in class as a one big unit and discussed the whole topic, but the application or the sequencing from plate tectonics would be to discuss earthquakes and also volcanoes, which we did in a different unit. So a little recap on the Earth's interior, looking at the upper mantle here in the diagram, and upper mantle contains both the asthenosphere, which is right here, looking at the lithosphere, and as a part of the lithosphere we have the crust. The two types of crust, which would be oceanic, which is the thin, more basaltic, and continental, which is the thicker, generally more granite and andesite. Then we have the moho, which is the kind of separating point in terms of speed of velocity of seismic waves between the crust and the mantle. And we also have the definition of what a tectonic plate is, which is the combination of both lithosphere and the crust that is a plate. I mean, the plates are broken into major and minor and micro based on size. And we have the plate boundaries, we have the composition of the plates and the densities, which would lead to both the isostasy and subduction rates and different zones of subduction and active and passive margins. So the key is the asthenosphere right here, and we have these arrows indicating there's movement. This is a plastic region or plastic zone whereby the temperature is high enough to have partial melting, and the circulation of plastic or semi-solid material, rock material, around in a convection current cycle. This would then actively move the crust and the plate in a certain direction. That would add the stress and energy into the plate, which contains both lithosphere and crust, and this area obviously is solid. So this solid, more brittle zone of rock being moved by the underlying asthenospheric convection currents with continuous stress and energy being added from those convection currents is going to be where you get the energy to break the rock, and once you've broken the rock, you can then look at discussing earthquakes. So it all comes down to the origin of plate tectonics. So we look onto stress in particular. Stress is the force applied to an area of rock. Now this force originates from plate tectonics and convection currents, and the fact that the entire crustal rock and surface of the Earth is being moved very slowly by underlying currents, with boundaries separating the plates and constant movement and geologic processes going along all the time, like subduction, like convergence, like divergence, and seafloor spreading. So the stress is the energy, and that is the building parts or how you make the earthquake, right? Because you need energy to be released. So the rock is going to be under stress and pressure. Now this can come in different directions. Now there are four main types of stress in terms of how the stress is applied to the rock in different directions. The first one is where you have a rock that's underground at a certain depth, but there's pressure and stress and energy being applied in every direction on that rock. This is called confining pressure or confined stress. It's also called lithostatic pressure, which means that it's a certain depth of rock underground, and the weight and pressure of the rock around it would apply the stress. Now this is a type of stress, but it does not cause fractures. So we don't really talk about it with earthquakes. It's just a very generic stress that we have to discuss. What you want to have is stress that turns into breaking the rock. Once you break the rock, that's when you have earthquakes. So we've got to discuss the other three types of stress. That's going to be tensional, which is where you're going to stretch the rock in opposite directions, where the stress is applied in a certain direction at a certain point. Compressional stress, which is to squeeze and compress the rock, again in certain directions. Then you have shear or shearing stress, which is to apply the stress on the rock in different directions, as you see from the diagram. Now all three, shearing, compressional and tensional, they all cause something. It's called strain. Strain is the effect of stress. You add stress, something's going to happen. Cause and effect. Well, what's going to happen is the strain. And strain's also called deformation. So it is the change of shape or size to the rock that is a result of the stress being applied underground. So where might there be compressional stress? Well, there could be compressional stress at convergent plate boundaries, where two plates are meeting and smashing together, like the Himalayas. Tensional stress would be where it's being pulled apart, so it would be a divergent plate boundary or mid-ocean ridge. And then a shearing stress would be associated with a transform plate boundary, where two plates are sliding past each other. So once you have stress, you have to look at strain and deformation. That's the result of stress. Now this diagram on the left is showing you the stages or the different parts of deformation based on the amount of stress applied to the rock underground and the strain. We have these different grades and levels of deformation. First one is elastic. Now this is like a rubber band. It's elastic, it's bendy. You add stress, the stress goes away and it goes back to normal. So exactly like an elastic band or rubber band or scrunchie. So it is elastic. So you add the stress and then it goes away. And the rock doesn't really break, it just bends and goes back. Now that happens with small stress, low stress, and low strain. And there's a limit to how far that rock can do this type of deformation before it goes into the next level, the next grade, which is called ductile. That's where the energy and stress is increased so that the rock will be permanently bent. There is permanent strain. So this area right here, going from the elastic limit to this limit up here, this is where you have permanent strain, or where the rock is now permanently bent and deformed. It doesn't go back to its original shape. Then we keep increasing the stress and we get more strain and more deformation, and we come to the third level, which is called brittle, which is what our upper mantle and especially the crust, the top 20 kilometers basically of the crust, the surface where we live, this is especially brittle. The deeper you go into the earth, the more heat is applied and you get more of a ductile and elastic properties to the rock because of the temperature as you increase depth. But towards the surface where it gets colder, you get more brittle rock. And this brittle deformation means that it's going to break easy. Now, so some rocks might go from elastic straight to brittle, or they might go from elastic to ductile and then to brittle. Some might just be completely brittle and have no elastic or ductile properties. It's just simply you add the stress and that rock's going to break. And again, you can add the stress in different ways, tensional, compressional, and shearing. But the brittle is important because that provides us with a break in the rock. So simply you have this rock right here. It's brittle in nature with the properties, and as soon as you add the stress, it's going to make a crack or a break, and this is called a fracture or a rupture in geology. And the important thing is this fracture and rupture if there's still, after it breaks, if there's still stress applied to the rock in certain directions, whether it be compressional, tensional, or shearing, there's going to be movement because the stress is going to create movement. It's what caused the fracture to break in the first place and go through different levels of deformation. If there's still stress, there's still going to be movement, and the movement is going to cause this fracture to become a fault, which is what we want to see if we're looking for earthquakes. So once we have our fracture, we have our fault. We can then discuss earthquakes and looking at the anatomy of different faults, the types of faults, how it relates to a transform plate boundary and how it relates to a subduction zone. We can also look at how to find the footwall and hanging wall on a certain type of fault. So a fault, again, is the movement around the fracture, which is going to cause energy to build up within the rocks because of the stress. And the key is when, let's say, this side's going to move and this side's going to stay still, that this kind of fracture right here, this fault line, is not perfectly smooth. It'll be like this. So there's a jagged or rough edge in which separates the two sides of the rocks, in this case the rock block diagram. And when the left side's going to move, it's going to get stuck. Once it gets stuck, the energy builds up, and there is a fight between the energy in the rock and the willingness to move the rock versus the friction between the two caused along the fault line that's going to stop the movement. So there's it's like having a car where you put the e-brake or the handbrake on and then you put it in gear and press the accelerator, right? The car wants to go, you're pressing the accelerator, you want to go fast, but you have the e-brake or the handbrake on and the car is locked and is stopping. So as soon as you let go, depress and let go of the e-brake or handbrake, that car's going to fly forward. It's exactly the same principle happens in an earthquake. You get the sticking of the rock along the fault line, the energy builds up, and eventually it's going to move, slip, or have displacement and have an offset, and it will release that trapped energy, exactly like what happens to the car. So here's our fault line. And if we're looking at trying to find the footwall or the hanging wall, what we have to do is put an X anywhere along the fault line or the fault plane. The plane is the surface in geology, so this would be the fault plane. And you put a X marks a spot. Then you draw straight lines down from the X and you figure out which side those arrows are going on. So they're going on this side, right? They're going on this side, the right side. This is the footwall. That's the footwall. The left side will have to be the hanging wall. Now, why is this important? The hanging wall is the side that moves in this type of fault line, in this type of fault. Now, this hanging wall can move up or it can move down. Now, I'll discuss the fault types in a second, but this is how you find the hanging wall. So in terms of the anatomy of a fault, we have the fault line right here. That's going to separate the left side from the right side. Now we know that we can do this and find this is going to be the hanging wall, and this is the footwall, and this type of fault line. We also have this exposed area of rock along the fault plane. That's called a fault scarp. We have the fault plane, which is this kind of like line going down through the fault. We also have the horizontal plane as well, which is usually the surface, and we can figure out the inclination or the angle of the fault line based on the angle right here. We also have the strike, which would be how far it's moving perpendicular to the horizontal and the fault plane. So the strike can be the displacement and movement. You can also look at the heave and the throw, which is how far it's going to go down and how far it goes across, the movement, the distance. We can also look at where the focus or the hypocenter is going to be, because that is really where the earthquake originates or begins along the fault line. So this would be a certain depth, and let's say right here. So this would be our focus and hypocenter, and then directly above it, for locating in terms of maps, we'd find the epicenter. The epicenter is directly above the focus and hypocenter, which is where the earthquake begins along the fault line at a certain depth. Now, if it's at a certain depth, we can classify it as a shallow or a deep earthquake. Now, the boundary of how to say it, the depth boundary of shallow versus deep is discussed in various textbooks and literature with different values. Some say as deep as 70 kilometers would be the boundary between shallow and deep. So if it's a 10-kilometer depth earthquake, it's generally going to be shallow. If it's a 100-kilometer depth earthquake, let's say a subduction zone, that's going to be generally a deep earthquake. Why do we not know the depth? The depth corresponds to potentially how much shaking and energy is felt on the surface, which is what we care about. Some of the deeper earthquakes we can't feel, so it's not as important, but the closer the earthquake gets to the surface, the potentially stronger the vibrations and shaking caused by all the waves, especially the L and R surface waves. So in terms of a transform plate boundary, you have here the fault line. As you see, it's vertical, so it'll be a different kind of fault. And we have our shearing stress, where the opposite directions or force is applied in a shearing effect. And you have the two plates that are moving parallel beside each other, sliding past each other. And this is a classic example of where earthquakes can form. And the classic example is the San Andreas fault line in North America, which separates the North American plate with the Pacific plate. And you get this 800-mile long area of transform plate boundary. So here are the different types of faults. Now, I've added 6 classic types here. There are some different ones that are very rare, but these are the 6 common ones that you'll find. Now, the word dip, that's going to mean angle, the angle of inclination. So that's looking at these two. So they're going down this column, 2 left-hand side diagrams, these rock diagrams, is going to be dip slip. So you have this fault line, which is outlined in red, and it's an angle. Here's our horizontal plane, here's the fault plane, and here is the angle. Now, the dip refers to the angle or inclination. It could be between anything from 1 degree down to 89 degrees. And I'll get to why that is. Now, if it's around 45 degrees, which is usually what it is, then it's just a regular dip slip. Now, the hanging wall, which again we know how to find, is the one that's going to move. Now, there's 2 types of movement. There is up and there is down. If the hanging wall will go up like this, okay, move up, we call this a reverse dip slip. And the stress that's going to cause this rock to move up is going to be compressional. So compressional stress will cause this kind of fault line to occur. It could be in a convergent plate boundary or some sort of orogeny and mountain building. Then you have the opposite way. The hanging wall will go down. This is called normal, a normal dip slip. Now this is caused by the opposite kind of stress applied different direction. So it'll be our tensional stress, where it's being pulled apart. So this would cause a graben, this would cause a half graben, this would cause a rift valley. This would be part of the Wilson cycle and how oceans form through rifting and breaking apart of crust, which is how Pangaea broke apart, and various continents floated away and drifted, like Alfred Wegener mentioned in his theory, and then the ocean floor, seafloor spreading of how Harry Hess and Matthews and Vines and discovered the mid-ocean ridges and looked at how the plates are created and then moved across the Earth's surface. So this would be tensional and a normal dip slip. If you come over here to the far right side, you have this top right, which is called a thrust fault. Now this is a dip slip, which is DS for short, and you'll see that the angle between the horizontal plane and the fault plane is a lot smaller. So this would be 35 degrees. So this would be called a thrust because of the speed or the velocity in which the hanging wall is going to go up. So it's a reverse dip slip. So there's going to be compressional stress applied to this part of the rock or part of the crust, and the fault line is at a low angle, which will enable there to be less gravity and less resistance when the movement up occurs, so it would move up quicker. So why we call it a thrust fault, which is really a very fast reverse dip slip. Then we have strike slip. Now strike slip is a classic transform plate boundary because you have this vertical fault line. See, it's different from the dip slip. Vertical fault line, and it separates the rock sides into left and right. Now, this version up here, the top one, is going to be a left lateral strike slip. It means the left side is going to move. This side is going to move. And the stress that's applied to this rock to cause this movement is usually flat horizontal movement, and this would be shearing stress. So like this. So it's not up and down, but it's side to side horizontal. Left side moves or the right side moves. So one side is going to move with a vertical fault line. This is called a strike slip. Now, strike would mean that there is a large movement or displacement, and the slip just means the offset, how far that rock's going to move. But the strike just also means it's sudden, very sudden movement. And the last type, we have oblique. Now, oblique is generally going to have a inclination like similar to dip slip. Like dip slip means like this, and strike slip means like this. So dip and strike. Now, oblique means it goes in between both the dip and the slip. Now, this also means there's two movements. So two times movements. So you're going to have either a reverse or normal dip slip movement in this oblique fault, but also you're going to have a portion of strike movement in this thing. So there's two movements. Could be either reverse and strike, left or right, or could be normal dip movement plus left or right. So there's two movements involved in this fault. So we have our rock profile, we have our fault line. Let's just say we draw a dip slip. And we have our focus or hypocenter. And we have our epicenter. This is the point where all the energy that's stored, whether it's in a dip slip or strike slip, is going to be released suddenly where there's displacement. So one side's going to move, it's going to release all that trapped energy that has overpowered the friction to cause the movement and displacement in the first place. And all that energy, the elastic energy, will be released through the rock in all directions, and the energy is going to propagate, which means move in a certain direction, propagate out through the rock, through different densities, different layers, through the earth, and cause the ground to shake, cause the earth to vibrate and shake for a certain time, and we know this as the earthquake. So the seismic waves are the name we give for the energy released by earthquakes. When you speak and you make noise, we call those sound waves. When you turn on the radio in the car, those are radio waves. Seismic waves are just a type of energy created by earthquakes and the displacement of rock underground at a certain depth along the fault line. So as the earthquake occurs and happens, you get these seismic waves which are going to come out of the focus in all directions at different speeds. Now, when every earthquake happens, with big earthquake, small earthquake, you get 4 waves released every time. And the 4 waves are right here. You've got primary, secondary, love, and Rayleigh. Now we separate these 4 waves into 2 distinct categories. Now the primary and the secondary, they're called body waves. Why we call them that? They go through the body or the interior of the earth. Now, primary waves, they are special because they propagate in a certain way. So look at the P wave. The P wave is the primary wave. And we call it the primary wave because it's the first wave that is received by any seismograph or seismometer that is near or close to the earthquake that receives the shaking. The P wave causes, all these waves cause shaking, but the P wave is the fastest, therefore it's the first one to be received by any seismograph. It's linear, which means it goes in a straight line, so there's a straight line energy. And also is why it makes it so fast. This is between 6 to 8 kilometers per second, and it is a compression and expansion type propagation, like a slinky, and it moves in one direction. That's why it's so fast. Then you get the S wave. The S wave is a little bit different. It's still a body wave, but it is a transverse wave, which means that it moves perpendicular to the direction of propagation. So I think of it as a snake. So there's our straight line, but it moves up and down, and we get some amplitude, and the crest and the trough, like a classic energy wave, but you get side to side movement, which makes it a little bit slower. So it's between 5 to 7 kilometers per hour. So it's secondary, so it's received second behind the P wave. Now, the cool thing about the P wave is it goes through any rock, any density, liquid, solid, you name it, the P wave goes through it. So if there's an earthquake in California, the P wave will be felt around the world in certain areas. Now, the S wave, yes, it goes through a lot of the rock, the solid rock, but when the S wave goes down to the outer core, the core mantle boundary, the outer core is liquid. It is a liquid state of matter. So when the S wave, because the way it moves, its particle motion is a certain way, when the S wave hits the outer core, hits the liquid, because of the way it moves, because it turns corners, it doesn't have enough energy to transfer or move from particle to particle when it turns to the outer core and it's liquid. Because of liquid, the particles are further apart. It's spaced. There's a larger distance between each particle, meaning that the energy can't flow between, and when the S wave hits the outer core, hits the liquid, it literally dies. The energy dissipates immediately and the S wave ceases to exist. So the outer core acts as like a little umbrella or a barrier for the S wave, but not so much the P wave. So then you have the two last waves, the Love wave and the Rayleigh wave. Now these are called surface waves. Why? Because they go through the surface of the Earth. They go from the focus or hypercenter straight up to the surface where they resonate and vibrate and move along the surface, along the top layer of the crust, and these waves cause the majority of the damage. So you see these horrible images of these areas affected by earthquakes like Haiti and Nepal and California and Japan. You're usually seeing the effect of the surface waves, the L and the R wave. So the L wave stands for love, based on the person who found it, discovered them, and they go again in a side-to-side kind of propagation. But for my class, to differentiate between the L and the S, I also like to say that they go in an up and down motion, but really they go side to side as well, similar to the S wave. But these goes through the surface. Now the R wave, they're kind of unique because they're going to go in this big orbital motion or circular motion. And the cool thing is that when these waves are released by the earthquake at the same time as the P and S wave, these move slower, 2 to 4 kilometers per hour, compared to the faster P and S waves. They go only through the surface, so they are more concentrated on an area, which causes more damage. They're more amplitude, more energy, but they actually combine. They combine and move through the crust together. So at the same time, the ground's going side to side, up and down, and in a big orbital motion. So these two, when they combine, cause a lot of damage. So we look at the propagation of these seismic waves. We're looking at really the P and S wave that's going to go through the interior layers of the Earth, and look at this kind of diagram where the star right here, that is the epicenter, and we have the main layers, the chemical layers of the Earth's interior. With the inner core, outer core, lower mantle, which is mesosphere, asthenosphere, lithosphere, and crust, the 6 in total. If we look at our P wave first, and you start with our epicenter, the P wave goes at a certain speed through the rock densities. And as it goes through denser rock, it will speed up. So it moves like this, and it curves around. And you can feel it in different parts of the world. So it happens in California, you might feel it in Chile or Chile, you might feel it in Argentina, you might feel it in New Zealand. But there's a certain area of the Earth where you won't feel the P wave, because when the P wave goes down and it hits the outer core, the core mantle boundary, because the outer core is liquid, it actually slows down, takes its time, goes a bit slower through the outer core, and then comes back out to the core mantle boundary and then speeds up again. So there'll be an area, an amount of degrees around the surface of the Earth where the P wave would not be felt, and we call this a shadow zone. Like creating a shadow with a tree. And because you have consistent velocities of this P wave through consistent densities of the Earth, we can generalize and have an average shadow zone that is created on both sides, on this side of the earthquake and also on this side where it hits the outer core, slows down and speeds up. So again, there's a shadow zone right here. So this goes from around 104 degrees up to about 140 degrees on either side. So there's an area of shadowing where there's a house or a person, and this location, like right here, they would not feel the P wave because of the interaction and influence of the outer core being liquid and changing the velocity of the waves, causing this spacing out of the wave, and you're not feeling it in the 104 to 140 degree angle. The same situation happens with the S wave, whereby you have the S wave traveling through at a certain speed, certain velocity through different rock densities. But when it hits the outer core, which is liquid, the wave actually ceases to continue through the liquid and dissipates immediately into the solid rock, the lower mantle. But it does create this very large shadow zone. So from there to there. So all of this will be considered a shadow zone blocked by the outer core, where this S wave cannot be felt anywhere along this large shadow zone. So as like the P wave, it starts at around 104 degrees, but extends all the way around to the other side, which is 104 degrees. So it's roughly a 150 degree angle from 104 to 104, which is going to be in this S wave shadow zone, because the outer core is liquid and the S wave cannot go through this liquid. Now, the important time and velocity difference. So the P wave and the S wave go at different speeds. The P wave is faster at 6 to 8 kilometers per second, and the S wave is a little bit slower from 5 to 7. So there's a definitive or definite speed difference between these two waves. So if you're standing on the surface and somewhere in the distance is the epicenter or the focus or hypocenter where the earthquake happened, and the waves are going to travel to you, right? So the P wave is going to travel to you. It would arrive first. You would feel the shaking from the P wave first. And then second, after a little while, in comes the S wave. And that comes in second because it's slower. But there is a time difference between the arrival of the P wave making you shake and the arrival of the S wave making you shake. And this time difference can be used to locate the earthquake. So in order for us to calculate where the earthquake is, we need an instrument or a piece of equipment that would allow us to record the shaking. This is called a seismometer. Now, this was originally made in a very basic way by the Chinese 2,000 years ago. However, the modern day seismometer was invented or reinvented in 1890 and has been developed ever since up to modern day seismometers, where they can be very accurate and really capture the energy and amplitude of the earthquake as it hits a location. So very simply, you have this structure holding up a wire or a string with a weighted ball here and some sort of pen or marker that would be touching a piece of paper or a piece of paper. Then as the piece of paper is attached to the ground or in the ground, so when the ground starts to shake and vibrate, the paper is going to be moved along at a certain time. So it's moved along with time, and there's time indications along the paper. So we can see when it started, how long it lasted for, and when each wave arrived. But the weighted ball would kind of stay stationary through gravity and allow the paper that's attached to the ground to move and kind of simulate and show the movement of the ground. So the larger the vibrations, the more the pen is going to move on the paper, which would show the scientists the amplitude of the earthquake, which is the amount of energy that's going to cause the magnitude, which is basically the size, and the amplitude is the height of the shaking, and it's seen by, small heights versus the larger heights over here. And then based on the magnitude and size and the energy that is producing the shaking, obviously, the more energy, the larger the shaking, the larger the earthquake. Then you can also see the intensity, which is going to be the amount of shaking, which is directly linked and proportionate to the amount of energy. And that would link up to the height of the vibrations and movement of the pen, which is the amplitude. Now, This is a seismometer, but you have the seismograph, which is the unit right here, but also this is called the seismogram, which is the actual recording of the earthquake shaking, the seismogram. So what I've drawn here is 3 seismograms made by 3 different seismometers in different locations. So location 1, location 2, location 3. Now, I'll get to why we need 3 locations in a second, but looking at the seismogram, you have this background vibrations that happen pretty much all the time. And then what happens is, after a certain time, you have the P wave arrive, which causes larger shaking and a higher amplitude of energy waves, as shown here. So the higher the waves go, the more energy, the more amplitude. Then the P wave comes and goes, and there's a little time difference, a little time interval from the P wave until the S wave arrives. Now, both of these are body waves. The P wave comes first, and then S wave comes in second. And there's a time difference from when the P wave arrives to the S wave arrives on the seismogram, because it records time as well as the shaking. So the S wave comes in and has its amplitude higher and energy, and then a little break, and then in comes the more dangerous, more damaging surface waves at that location. And it's repeated in location 2 and location 3. However, the difference is, because these are 3 different locations, we're not exactly sure where the earthquake originated from or came from. But these locations all record the same earthquake. This is the same earthquake. The P wave and S wave at location 2 and the P wave and S wave at location 3. As you can see, they seem to have different time intervals. So we can use these 3 different time differences between the P and S wave. Let's say location 1 has a time difference of, let's say, 10 minutes. And location 2 has a difference of 3 minutes. And location 3 has a difference of 5 minutes. So we use our seismogram information, our details of when the P wave arrives and the S wave arrives from our 3 locations onto a generic, very average time travel graph used for all earthquakes around the world, and it's showing you the time in minutes versus the distance, usually in kilometers or miles, and it's showing you the P wave and the S wave. Now you can see that the P wave is going to be faster because it arrives at a certain location, certain distance from the epicenter at a faster time than the S wave, same distance but a longer duration. So the P wave is going to be quicker. Now you can see there is a gap that opens up between the P wave and S wave in time that increases the further away you go from the epicenter. So if you were, let's say, 10,000 kilometers away, there'll be a long wait between the P wave arriving and then the S wave arriving. Whereas if you're 10 feet away, it'll be kind of more instant. Both arrive at the same time. So we can use our seismogram information from our 3 locations on this graph to figure out where each location was in respect to the epicenter, how far away they were. So the first one was 10 minutes. So we've got to find where there is a 10-minute gap between the P wave line, this red line, and the S wave line, the yellow line. So all we do is we find a 10-minute gap, 10 minutes, how far 10 minutes is. So let's say this is 0 minutes, and this is, let's say, 10 minutes. That's a 10-minute gap. You move that over to the line, and let's say it is here. So this right here is a 10-minute difference. All you do is go down vertically, down to the distance, and let's say it gives you a distance of 8,000 kilometers. So for location 1, the distance is going to be 8,000 kilometers. For 2, it's going to be 3 minutes, which is right here, down, and it's going to be 2,000 kilometers. And for the location 3, 5 minutes, right here, it's going to be, let's say, 5,000 kilometers. So we have our locations on a map, and we have our seismogram information finding the time difference between the P and S wave. Using that on the time travel graph to find the distance, we can triangulate using 3 locations to find the exact location of the epicenter. So location 1 was 8,000 kilometers. So if I draw a circle around 1 that is a radius of 8,000 kilometers, what it's saying is that anywhere along this red line on the map is where the earthquake could be, the epicenter could be. We're not sure. We've got to basically use more circles to narrow down where it is. So 2 was a 2,000. So if I draw a 2,000 circle, we have two possible locations, over here, and over here. So two locations using two different seismogram data. But we need one. So we add in this third location, which was 5,000, and what we get is, we get this. So this is our 5,000. Obviously it's not to scale, but what it's showing you is that when the three circles are drawn, using the distance from the epicenter that you found in the time travel graph and the P and S wave time difference, you get one location, which is right here, and this is our epicenter. This is where the earthquake happens, where the earthquake occurred. And this is called triangulation. So we've looked at the epicenter and locating the earthquake. Now, how we measure the earthquake. We discussed the seismometer, which was discovered in 1890 and then redefined and made more accurate through the decades. But there were certain events that really transported seismology and the understanding of earthquakes into new realms. That was the 1906 earthquake in California, centered around the city of San Francisco in the Bay Area, and it was catastrophic. It was the earthquake that really took America by surprise because it hit a major city and caused so much damage and death and destruction and costs of repair. But it also gave scientists in California, especially, and seismologists, the ability and the opportunity to study a large earthquake up close and personal and generate a lot more data, information, and ideas about what these earthquakes were, why they shake the ground, how long they last for, and the seismology of the earthquake. So the functionality, how it actually works, the processes that are going on within the earth. And this led to, so in 1908, just 2 years after the earthquake, there was the Lawson Report, which was researched and reported about the earthquake and the effects and the damage and the functionality of the earthquake. And then in 1910, Reed formulated his theory on elastic rebound. So he's called it ERT for short. Now this was the simple way of explaining how earthquakes work and why we get what's called a foreshock, which is a small release of energy, a small release of seismic energy before the main event. So you got the main earthquake, which could be on a different scale or size, and then you have what's called the aftershock, which is a time lapse, could be a few seconds, few days, few months. There will be a release of the last energy amount that's stored in the rocks. Now this could be a larger earthquake, could be a small earthquake, but it could happen after the main event. So aftershocks can also be very, very dangerous. And this elastic rebound theory explains how this works, based on the storage of energy, the sudden release of energy, and the dissipation of energy through the rock, and how it shakes, and how it realigns itself and rebounds to a certain position after the offset and displacement, which would cause both the foreshock, main event, and the aftershock. So we have the Mercalli scale, which is used basically for analyzing the damage curves from an earthquake, and that goes in Roman numerals from 1 up to 12, 12 being the most damage, 1 being very small, minor damage. And you also have the modified Mercalli, which was just going to be the more advanced version of the original Italian seismologist scale. And this is used, again, just for the damage. But it's going to be the more consistent and aligned damage scales. Then we have the very commonly used, more scientific, more detailed Richter scale. So this was 1935. And based on Charles Richter, his scale from California, and it was from 0 to 10, and it has a scale based on the magnitude of the earthquake, which is the size, and this is based on the energy, based on the physics, based on the motion and vibration and movement of the ground, and 0 being very, very small and nothing, 10 being catastrophic and world event, so very, very bad. And below a 3 or 3.5 is humans can't really feel it. And then above a 3.5, obviously you get progressively larger vibrations and you feel it. And obviously the damage would entail. And then you can also combine this with the Mercalli scale. But really The Richter scale, which looks like this, would be a big M, capital M, and then 7.0. This would be the normal way to categorize an earthquake. Now, this scale is logarithmic, which means that for every increase in scale number, you go from 1 to a 2, that will be 10 times the shaking. However, and also to get the 10 times shaking, you need to have a lot more energy. So it's around 31 times more energy released to cause a tenfold increase in the shaking. So magnitude 2 up to magnitude 5 earthquake would be a lot larger. A lot larger. It would be 1,000 times more shaking, and you can imagine that's exponentially more energy involved and released to cause that shaking. Then we have the moment magnitude intensity scale. This one is the most or highest accuracy, is the most scientific, and it basically looks at different seismic waves or seismic moments based on location, depth, and distance, and really does categorize each earthquake into each section so it makes the most accurate magnitude scale possible. So looking at the hazards that are associated with earthquakes and the shaking that comes with earthquakes in different magnitudes and sizes and energies. So the hazard generally is anything that is going to be destructive. Anything that poses a threat to both society, for humans, and for our way of life, and for anything to do with living our lives and the environment, both the natural environment and the built environment. So it depends on where the earthquake hits, how close it is, the intensity, the duration. The average earthquake lasts a minute, and obviously the rock type and the amount of intensity that that earthquake produces will directly influence the hazard, and also the amount, also where it hits. Is it a wealthy area that can afford better engineering standards and building codes and the understanding of an earthquake and how it reacts to different kind of buildings, or a very poor area where they can't afford to take that kind of consideration when building structures? It's just simple design, simple materials that are going to fall down. So we're looking at primary as something that happens initially, that is more immediate, more of a direct relationship to the shaking. So that could be temporal, or could just be a cause and effect. Now, the secondary hazard will be something that will be long-term, that could be caused by the primary hazard. So, for example, the built environment. The primary would be structural integrity is compromised because the structure is being shaken, cracks appear, the building starts to break and be destroyed. The secondary hazard would be loss of people's businesses, people's homes, structures, infrastructure and utility buildings, and the breakdown of the economy due to the damage to the buildings and the roads. So there's the immediate effect and the long-term effect, the cause and effect, so primary and secondary. We can break down the hazards into these different categories. So the natural environment, which is going to be the landscape, the terrain, the relief, the biome or the ecosystem and how it affects the animals, how it affects the food webs and food chains. That could be both primary and secondary. The built environment, that's anything to do with the human side of structures, and that can go as easy as a building or a house or a place of business to a road or infrastructure, railways, subway tunnels, bridges, overpasses, underpasses, you name it. Anything built by humans can be affected by earthquakes and fall down or be destroyed during an earthquake is considered here in the built environment. So as big as a city or as small as a village. Either way, it is a built structure. Then looking at the human interaction, so the immediate issue to someone's health and safety, from the falling over and scraping your leg to, unfortunately, the worst part is death. And there's a large death toll caused by the earthquake. And there's various levels in between that. Now, this would relate to the built environment with the access to emergency services, EMTs, nurses, doctors, firemen, policemen, the access to roads and evacuating the area, to how fast we can get to people who are perhaps maybe buried under rubble or debris because of the structural failing of houses. Look at the economic impacts. There can also be long-term effects to the local area's industry, financial sector, businesses, poverty rates, unemployment, and all these things can be looked at in separate categories. Yet when you're looking at, let's say, a big city, let's say it hits a big earthquake hits LA, you're going to have to discuss each one, but then combine all the different categories into one, because LA has a mix of not only a large population, very densely populated area, but you also got the natural environment, the economic side, and the long-term aspects of trying to rebuild an area like Los Angeles, which would be an exceedingly amount of money. One earthquake hazard in particular we have to cover is called liquefaction. Now, this is a term that is related to the effect of seismic waves going through a landscape or an area or region on the planet, which has changes to the geologic surface. So if it's either soil surface or loose or unconsolidated sediment, or maybe, let's say, stratified rock layers like sedimentary rock, like sandstone or conglomerate or limestone, you are going to have a change to that surface because of the seismic waves and the shaking of both the L and the R waves. So this liquefaction is really just the changes to the stability and strength of the rock with the water in the pores in between the rock, and how the particles are going to be spread apart because of the movement induced by the seismic waves, and this decrease in strength of the surface caused by the waves and the composition of the ground is called liquefaction. And this is usually where whatever's on top of the surface, be it a road, a car, or a building, would slowly sink into this now liquid or semi-liquid material because of the effect of the seismic waves and the water, making this rock become more liquid or behave more like a liquid. Now, this is dependent on, obviously, the rock type, the soil composition, the amount of water, and the porosity of the rock material, the height of the water table, which is to do with the precip and the season, the climate, and also the location and how long the earthquake shaking is going to occur for, the intensity, magnitude, and the classic example would be with the San Andreas fault line and the quakes in San Francisco, whereby the ground closest to the coastline actually turned into this liquefaction and caused damage through the sinking of buildings into the ground. Now we have one of the most famous hazards associated with earthquakes. Besides the actual earthquake destroying things, the earthquake can also cause a tsunami. Now, the tsunami is a Japanese word, means harbor wave, and the definition for me in class is that the ocean floods the land. We have to really stress this is not a single wave, like an ocean wave, which is wind generated, nor is it a tidal wave, which is induced by the tides, which is the gravitational pull of both the moon and the sun as the earth spins on its axis. This is a tectonically created wave with a very long wave period, and it operates in the ocean, so you can call it an ocean wave, but really there is a definitive difference between ocean waves caused by wind and tsunamis. So a tsunami wave has the longest wave period and has a lot of energy that transports a large section of ocean as one unified piece from the ocean onto the coastline. As it approaches the coastline, you're going to have this uniform wave, but then as it reaches the coastline with decrease in water depths, the increase in friction off the ocean floor, the topography, the relief, and how shallow it is, how it changes with maybe undersea canyons or reefs or barrier islands or sandbanks or shoals, you're going to have different kind of wave approaching the coastline, and the energy is going to change. So the wave height could also change. So these tsunamis transport a lot of energy onto land, and the distance it will go on land would depend on the elevation, the gradient of the land, the closeness of any kind of high elevation or mountains or hills to reflect off, and also the amount of energy initially in the wave being transported onto the coastline and how it dissipates. Now, these waves are sinusoidal in nature. It means that they have a regular wave pattern of oscillating repetitive wave pattern through the ocean with a very small wave height in open ocean. When the wave gets closer, as I mentioned before, it does change its size and the energy does kind of like bunch up and create this large energy transport on land. So tsunamis can be caused obviously by a plate boundary whereby one of the plates would be forced upwards through a displacement and offset. You can also have a tsunami caused by a landslide, both submarine or underwater landslide above the ocean surface landslide, let's say with a volcanic eruption causing a landslide like with Mount St. Helens, and a large amount of rock would flow into the water. You can also have carving of glaciers could cause a tsunami as well. It's just the sudden displacement and movement of a lot of water, generally caused by tectonic processes. So what this earthquake review has done has taken you from tectonics and energy through to stress, fractures and faults, looking at seismic waves, looking at the seismometer and how we measure and locate the earthquakes using the PNS wave, looking at the time difference and the time travel graph and the distance from the epicenter and what a focus and hypocenter is, to the hazards, to the primary and secondary, and then also to liquefaction and tsunami as the big common hazards, and looking at the San Andreas fault line, looking at the Richter scale and different scales, how to measure the earthquakes. So hopefully this is going to be helpful for you for your test coming up. This is the Earth Science Classroom. Thank you for watching. I hope you enjoyed the content. Check out more videos on our channel and don't forget to subscribe. Thank you again.